Hello guys! Today we're going to be diving into the world of Sigmatropic rearrangements, which is essentially musical chairs of electron pushing. In this video, we're going to be going over 3 examples to help this concept stick. Concept number 1 will be a basic 3,3 Sigmatropic shift example. Concept number 2 will be the Oxy-cope rearrangement. And concept number 3 will be the Claisen rearrangement. These reactions follow a super clean 3-step pattern that I want you to keep in mind throughout the whole video. Step number 1 is going to be pick a pi bond. Step number 2 is going to be use that pi bond to attack a carbon, a part of a different pi bond. And then step number 3 is to break a sigma bond and form your product. And right now, if this sounds really confusing, that's okay. Hopefully by the end of the video, this will be very, very, very helpful. And I guess this wasn't 3 steps. It's technically 4. But without further ado, let's get into the video. But please, if you find my content helpful,
just leave a like, comment, save, and or subscribe to my channel. It means the world to me when you guys give me feedback. And it really helps the channel grow and keep the chemistry alive.
Let's get into the first example. All right, guys, let's start with our first example. Remembering those 3 main steps that I just told you. So step 1 is pick a pi bond. So let's say I pick this pi bond. That's step number 1, pick a pi. Step number 2 is always attack another carbon, a part of a different pi bond. So this pi bond could go and attack that carbon because it's a part of a pi, right? This carbon is sigma and pi bonded to another carbon. So this is attack C pi on a different pi. But now, in order to avoid breaking the octet rule, right now, if we just drew a bond to this green carbon, well, that carbon would end up having 5 bonds because it also has 2 hydrogens. And then we would break the octet rule. So in order to not break the octet rule, what we need to do is move these 2 electrons over. Oh no, but that means this carbon would end up breaking the octet rule, right? So what's step number 3? Step number 3 is break the sigma. And it's always going to be the sigma bond that exists in between this carbon, the carbon that is now going to end up having a pi bond, and the carbon that's directly attached to it. So the 2 electrons in this sigma bond are going to have to go 2 over. Those electrons are moving towards the carbon that initially had electrons stolen from it. So that would be this carbon right here. Because this electron, this pink one, moved over there, so it lost an electron. So in the end, it must gain that electron back. And boom, you get your new structure. So let's draw this, okay? I'm going to draw everything that did not change. So this bond didn't move, this bond didn't move, this white bond didn't move, neither did this bond. But now, in between this carbon and this carbon, there is a pink bond. And in between these 2 carbons, we have a new purple bond. And now in between these 2 carbons, well, the 2 blue electrons move there. And that's pretty much it. That would be your product of the Sigmatropic rearrangement. So now I told you at the beginning of this video that this would be a 3,3 reaction. Why is that? Let's go back to the very beginning. And let's go over how to name this reaction. So I'm going to redraw our starting material. We're going to break up naming this rearrangement into 4 simple steps. Step 1 is going back to your starting material. Step number 2 is to find the sigma bond that broke. So this sigma bond broke. So find it, chop it in half, and label each carbon a part of that sigma bond 1, 1, and 1. Now you have to count outwards on each side until you reach the carbons that ended up forming a new sigma bond. So the 2 carbons that ended up forming a sigma bond were these 2 carbons. I need to count outwards until I reach this carbon and that carbon. So 1, 2, 3. 1, 2, 3. So since this carbon and this carbon formed a sigma bond, this would be a 3,3 Sigmatropic rearrangement. Pause this video, rewind, and see if you could label this from the very start yourself. So this would be a 3,3 Sigmatropic rearrangement. All right, guys, so let's just break up the steps that we just went over on how to name a sigmatropic rearrangement. So step 1 is to go back to your starting material. Step number 2 is to find the sigma bond that broke. Step number 3 is to chop that sigma bond in half. And then step number 4 is to count outward till you reach the carbons that form the new sigma bond. All right, let's do our second example, which is an Oxy-cope rearrangement, which is also just a 3, 3 sigmatropic rearrangement. This looks pretty similar to the last example. But now we have an OH. Your steps stay the exact same. Step number 1 is always find that pi bond. Find the pi bond. Okay, let's say we pick this pi bond again. What do? Say it with me. Step number 2 is you attack a new pi bond. Attack a carbon, a part of a new pi bond, so a different pi bond. So let's say we attack that carbon. But now in order to not break the octet rule, these 2 electrons, the pi electrons, which are easily broken, can move 2 over. But now this carbon would have the octet rule broken unless we broke this sigma bond. Where does it need to go? Well, it needs to move towards the carbon that lost an electron to begin with, which would be that carbon. So we got to go 2 over. 3 arrows. Bada bing, bada boom. Draw your product. Draw in everything that did not change. So these 2 bonds did not change. These 2 bonds did not change. Now you have a new sigma bond, yay, drawn in pink. A new pi bond drawn in green. And another bond drawn in blue. And we have our OH group right there. It did not move. But right now we have the enol. And whenever you have an enol, well, tautomerization could take place. And then you would get your aldehyde version. And all that happens is the pi bond is essentially just going to do a little shimmy, shimmy, shift and move there. And the hydrogen is going to do a little shimmy, shimmy, shift and move here. And that's your aldehyde. Let me walk you through this little shimmy, shimmy, shift again. So the pi bond shimmy shifts from here. And the hydrogen shimmy shifts from there. And I forgot to draw in step number 3, which is to break your sigma. So our actual product is going to be the aldehyde after the shimmy, shimmy, shift, which is our tautomerization taking place. And this is your Oxy-cope rearrangement. So now if we had to name this sigmatropic rearrangement, well, let's go back to our 4 steps of naming. Start with the sigma bond that breaks. So this sigma bond breaks. Chop it in half, label each of those carbons carbon number 1. Then count outwards till you reach the 2 carbons that form a new sigma bond. So 2, 3. 2, 3. So this is a 3, 3 sigmatropic rearrangement because the new sigma bond was formed there. So this is a 3, 3 sigmatropic rearrangement. But because we have this tautomerization to the aldehyde, this is an Oxy-cope rearrangement. Tautomerization, which is a shimmy, shimmy, shift of a pi bond and a hydrogen. And then we get our aldehyde. This is the Oxy-cope. All right, guys, this brings me to my last example, which is the Claisen rearrangement. And it All right, guys, this brings me to my last example, which is the Claisen rearrangement, and this involves an aromatic ring. And it ends up being a 3, 3 sigmatropic rearrangement. Surprise, surprise. So step number 1 is pick a pi bond. Let's say I pick this pi bond. Okay, who do I attack? Well, you're probably not going to end up doing anything like this because, well, that's just aromaticity and that doesn't change anything. In organic chemistry, we always want to form a new product. So we wouldn't be forming anything new there. So what about a pi bond that's not in the ring? This guy. So I can go 2 in. Okay, well, in order for this carbon to not break the octet rule, well, then the pi bond's got to move. So we could go 2 over. And do you notice that I'm always taking these 2 electrons and I'm moving them in between the carbon that initially has these electrons and the carbon adjacent. I'm never taking these 2 electrons right now and like moving them 2 carbons over. It's always just 2 over, 2 directly over. And now in order for this green carbon to not break the octet rule, well, these 2 electrons, they got to move 2 over as well. So we got to break the sigma bond. This is our breaking the sigma bond. And where do they move towards? Well, they got to move towards the carbon that initially had an electron stolen from it. So we move 2 over. So what do we get? Play the game of draw in what did not change. So none of these things changed. Now we get an O, a new green pi bond. A pink bond goes there. I'm going to erase this hydrogen just for simplicity. There's still a white single bond there, and a white single bond there, and there's a blue pi bond there. Oh no, we broke an aromaticity. But what can you identify? The shimmy, shimmy, shift. We can identify a keto group, and a keto can tautomerize to the enol form, just like the enol can tautomerize to the keto. Well, the keto can also tautomerize to the enol. So if I do my shimmy, shimmy, shift in the opposite direction, well, there's a hydrogen here. So the hydrogen, I'm going to copy and paste this. And let's draw out the shimmy, shimmy, shift that I'm referring to. So the hydrogen is going to shimmy, shimmy, shift to the oxygen. And this pi bond is going to shimmy, shimmy, shift over in between the carbon with the oxygen and the carbon that lost that hydrogen. It's a shimmy, shimmy, shift, which is also tautomerization. So now we get our enol, keto, and then the enol. That's it for this video. I hope you guys found this video helpful. Please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. And yeah, if you leave a comment, they literally always make my day. I love to hear your guys' feedback. And yeah, it just warms my heart to see that even if this helped one person. I hope you have a great day. Goodbye.